minutes. All right, so continuing our discussion of continuity, we have two different types of discontinuities. So when we're not continuous at a point, so let's define that. Definition, a discontinuity at x equals a. So one of the three bullet points fails. Okay, first one is going to be removable if we can fix it. So removable if redefining it at x equals a can fix the discontinuity. So if redefining f at x equals a can fix or remove the discontinuity. So we'll look at an example of that. All right, so then that would be called removable. If you can't fix it by redefining at that point, then it's going to be called an essential discontinuity. Okay, so it's essential if it can't be redefined to remove the discontinuity. At that point, okay? So we had an example before of an essential one. So I think, what did we have? Well, let's just look at another example. If I have f of x equals 1 over x minus 2, what does that look like? Let's draw the graph. What type of shift is that of the 1 over x? Right or left or up or down? Right. It'd be a right shift because the denominator you plug in 2 to get 0. So at x equals 2, the domain of f is all reals except the point containing 2. And that's going to be a vertical asymptote, right? So this is also something that we were looking at in chapter or section 1.7. But anyway, so we've got this is x equals 2 is the vertical asymptote. And anyway, so we got something like this. I could actually have a scale. If I plugged in 0, I get minus a half, right, for crossing the x-axis. So I have a scale on both the x and the y-axis, actually. But anyway, this is discontinuous where? At x equals 2, right? It's discontinuous at x equals 2. So where is it continuous? We talked about continuity. You can draw the graph without lifting your pen. I can do that except for x equals 2. So I could actually say that this one is continuous on all reals excluding 2, which this is actually continuous on the domain of f, right? So what can we say about this function? What type of, this is a rational function because it's got a quotient in it. But anyway, we can say that this is a continuous function, isn't it? It's continuous on its domain. We can say that. So this is actually a continuous function. That doesn't mean it's continuous everywhere. That just means it's continuous on its domain. So one thing that I haven't said yet specifically is any rational function is going to be continuous on its domain because it's a polynomial divided by a polynomial. And polynomials are continuous where? Everywhere. So rational functions are going to be continuous everywhere where it's defined. So we got to exclude where you divide by 0. Okay. But rational functions are continuous on their domain. So their rational functions are continuous functions. All right. But anyway, does this make sense? If this is essential, there's no way I could redefine a single point f of 2 to make it where I can draw my graph without lifting my pen. You can't do it. even if both sides went up, like if I had 1 over x minus 2 quantity squared, how does that change my graph? It would make it go up here, right, like that. So I wouldn't have that down below. I'd have this. You're never going to close that gap in there. No matter how high up you get, no matter how close to x equals 2 you get on both sides, there's always going to be more than just one dot in between, right? So anyway, so this is called an essential discontinuity. All right, so hopefully that makes sense. So let's go back and look at the example we were looking at before. We were looking at, for a removable one, we had f of x equals x squared minus 9 over x plus 3. And so this is equivalent to x plus 3 times x minus 3 over x plus 3. And these cancel out, so that actually equals that. But it's equivalent to x minus 3 on the domain of f, right? Which is all reals except for where you divide by 0, which is -3. All reals except -3. All right, but it's the y equals x minus 3. It's going to look like that. We already graphed this. But anyway, so if you plug in 0, you get -3, don't we? And then where do I have a problem? I have a problem when x equals -3. What would it be? So negative, if I plug in f of -3, I get 0 over 0, right? Which does not exist. All right, so basically 1 fails. So it's discontinuous at x equals -3. So to show continuity, we have the 3 bullet points. F of a exists. The limit as x approaches a from both sides of f of x exists, and they're equal. Well, 1 fails here. 1 fails. So it's discontinuous at x equals -3. But the question is, can we redefine this in a way that makes it continuous? And the answer to that is yes, we can. We can fill the hole. What would this height be if it was at the hole? Well, if I plugged in -3 to what it's equivalent to, I get -3 minus 3, which is -6. And so I have a hole at -3 minus 6. I could fill the hole. -3 minus 6 is a hole here. So I could fill the hole. So it's removable if we can fix it, or what I call fill the hole. Fill the hole. Fill the hole. We're going to fill the hole. So how do I fill the hole? So we're going to redefine it as, so we're going to redefine f of x to equal x squared minus 9 over x plus 3 if x doesn't equal -3, right? And we're also going to define it to be a height. Remember, that's a height of -6 if x equals -3. So this is how I'm going to redefine this graph. That fills the hole, and it avoids the break in the line. Okay? So basically, a removable discontinuity, we can fill the hole. Okay? All good with that? So basically, besides finding out where functions are discontinuous and continuous, when we have a discontinuity, we want to know what type it is. Okay? So if it's an asymptote, most likely it's going to be an essential discontinuity. Okay? And just one more, going back to what an example we looked at earlier was f of x equals square root of x. At x equals 0, it's discontinuous, right? Because 2 fails, that limit from both sides doesn't exist, so 2 fails. So it's discontinuous at x equals 0. What type of discontinuity is it? It's going to be essential, okay? Because we can't fix it. There's no point. We actually have it defined at 0, but there's no other point that's going to make it continuous, because when we approach from the left-handed limit isn't going to exist because it's not defined. So anyway, this is going to be an essential discontinuity at x equals 0. Okay? So if you have essential discontinuities, if you have an asymptote or a stop, there's a good chance it's essential. If you have just a hole that you can fix by filling the hole, if you can fill the hole, it's going to be removable. And then we got to do some algebraic manipulation. Really, it's limit theory, right? We want to know what the limit is, and then if we can redefine it so it actually equals that, because remember, for continuity to point, you got to be defined there, and the limit has to exist, and they have to be equal. So basically, it's just a matter of doing all the manipulation tricks that we had before, trying to figure out what that limit is. And we factored, we multiplied top and bottom by conjugates, right? We did all kinds of algebra tricks. But we're trying to avoid plotting, plugging in points and stuff too. Okay. So hopefully that makes sense. And we'll go for about another 5 minutes here. So what is a rational function again? A rational function is basically q of x is going to be numerator function divided by denominator function, where n of x and d of x are polynomials. Okay, polys are continuous on all real numbers. So what would the domain of q would be the set of all x's such that the denominator is not equal to 0. So we got to exclude, basically it's going to be all real numbers except where you divide by 0. So we're going to figure that out. Okay. Anyway, so that's a rational function. What's going to happen is these are continuous on their domain. Because polynomials are nice and polynomials are continuous everywhere, rational functions are going to be continuous everywhere except for where you divide by 0, but that's on their domain. So what does that mean? What did we say? We say any function that's continuous on its domain is called a continuous function. Okay, so rational functions are continuous functions. Okay, and let's look at one example that maybe is just a tad bit awkward to figure out if it's removable or essential for the discontinuity. So first of all, f of x is I believe this is number 21 in your book, but anyway, it's the square root of 2 minus the square root of x plus 2 all over x. Okay, well, so one of the questions is, what is the domain of f? Well, we're going to have to exclude 0, right? Because you can't divide by 0, so x can't equal 0. But what else do we know for the domain? X plus 2 has to be greater than or equal to 0, right? So this has to be greater than or equal to 0, and this one in the bottom can't equal 0. So how do you do that? Just solve it. So if x plus 2 is greater than or equal to 0, so that I can take the square root, subtract 2 from both sides, that says x is greater than or equal to minus 2, right? Pretty simple to figure that out. So it's okay to equal minus 2 because I'd have the square root of 0 there. So anyway, including negative 2. Now we can't go all the way to infinity though, because what do I got to do? Exclude 0. So including negative 2 to not including 0, union not including 0 to infinity. Or if you'd rather call that r plus, you can. Okay, but there's no real shorthand to do this. You could also say the domain is negative 2 to infinity minus the set containing 0. That's a little bit more awkward. This is probably good enough, one of these two. Whether you go not including 0 to infinity or call that r plus, I don't care. All right, but anyway, so this has this is discontinuous where? at x equals 0 for sure, right? Because it's not even defined there. If I plug in 0, I get the square root of 2 minus the square root of 2 all over it, which is 0 over 0. So 1. What is f of 0? It equals square root of 2 minus the square root of 0 plus 2 over 0, which is 0 over 0. So that's indeterminate. Now, we looked in, when we're doing limit theory, 0 over 0 a lot of times was a whole, right? And if it's a whole, we might be able to fix it, right? But it doesn't have to be a whole. It could also be an asymptote, which makes it an essential discontinuity. It could also be undefined, right? So we need to find out what we have here. So anyway, this is indeterminate. So we need more information. So to figure out the type of discontinuity, okay, so I'll finish this example and then we'll be done. So I'm going to take the limit as x approaches 0 from both sides of the square root of 2 plus the square root of minus, the square root of x plus 2 all over x. How do I figure out what that limit is? You remember what algebra manipulation we got? It's 0 over 0, so we got to do something. Multiply top and bottom by the conjugate, which is the same thing with the opposite sign in the middle. So it's going to be a plus. So this one's a minus, so that's a plus. And what you do to the top, I also got to do to the bottom. Okay. And then when I do that on top, what do I get? Square root of 2 times square root of 2 is 2. And I get plus root 2 times root x plus 2 minus root 2 times root x plus 2, which goes away. The outer and inner cancel. And then plus times minus is minus. And then root x plus 2 times root x plus 2 is the quantity x plus 2. So I'm going to put that in parentheses, right? Because I'm going to subtract the whole thing. And on the bottom, I'm not going to multiply this out. I'm going to leave it factored because there's no real advantage to multiplying it out. Just so you know, you can if you really want to, and then you're going to want to cancel it back, factor it back out. Why? Because what I have on the right, I'm going to add the opposite here. So then the 2 and the minus 2 cancel, and I have a minus x on top. So what can I do now? I can cancel that minus x because it's multiplication. I can cancel this minus x with this x, and I'm left with a minus 1 on top. Right? So this is equivalent to the limit as x approaches 0 of minus 1 over the square root of 2 plus the square root of x plus 2. Now, can I figure out what it is? Can I plug in 0 here? Yes. And if I plug in 0, I'm going to get, so we got limit of the quotient is quotient limit, limit of the sum is the sum limit, limit of the root is the root of limit, and then polynomial we can plug in, but 0 plus 2, this is going to be minus 1 over the square root of 2 plus the square root of 2, right? What is the square root of 2 plus the square root of 2? Huh? 2 square roots of 2. So if I got x plus x, it's 2x, right? So anyway, this is 2 square roots of 2. So what could I do? What do you think? What type of discontinuity is this? Do you think? Essential or removable? Remember, it's removable if we could redefine f of 0 to equal some specific value that fixes it. So this actually is a whole because there's a real number output here. This is removable. And we could redefine f of 0 to equal minus 1 over 2 root 2. So that's a little more awkward one that allows you to kind of see how we figure it out. You got to figure out what the limit is. And then for continuity, you know, f evaluated at that point has to equal the limit, right? So we fill the hole by doing it that way. So it's okay to have that function everywhere to the right of -2, okay? And then it's not going to be continuous at x equals -2 because it's not going to have left-handed continuity just because of that square root or anything left of -2. It's not even part of the domain. It's not going to be continuous there. But this is a removable discontinuity, so we're good. Checking out.